Hi Chem students, today we'll be talking about orbital diagrams. Please get out your notes and turn to page 4 and get your periodic table ready. We will show with arrow notation how the electrons are arranged in atomic orbitals for a given element. Just like electron configuration, orbital diagrams start out with 1s, which has one orbital, and that is represented by either a box or a line as I've drawn here. Then we go to 2s, which also has one orbital. Remember, each orbital can contain up to 2 electrons. So I'm going to write 2s and a line. Then we would get to the 2p, and that has 1, 2, 3 orbitals. So that is represented by the 3 lines. Then we would go back to 3s, which only has one orbital again, and that would just be one line. Then if we go to 3p, that would have 3 orbitals. So I would write 1, 2, 3 lines for that. Now let's work on filling up these orbitals for carbon. Carbon is located right here on the periodic table. It's going to have 2 electrons in the 1s orbital. These electrons are shown to have opposite spins because they're occupying the same orbital. Then there would be 2 electrons in the 2s, represented once again by 2 opposite spin arrows. Then when we get to 2p, that will be 2p2 for carbon. So the first electron will go into the first orbital, and the second electron will go into its own orbital. Electrons prefer to be in their own orbital unless they have no choice but to fill up. And that's the orbital diagram for carbon because it stops at 2p2. Now let's do that again for fluorine, which go just a little bit further than carbon. Fluorine also has 2 electrons in 1s and 2 electrons in 2s. When you get to the p block, it's going to have 1, 2, 3, 4, 5. That's where fluorine is. So 2p5. Let's see how this fill up. So 1, 2, 3, each filling up their own orbital. And the fourth would have no choice but to be with the first. And the fifth will have no choice but to be with the second. Now pause the video and I want you to try magnesium and argon by yourself. Welcome back. Hopefully you have gotten these orbital diagrams for magnesium and argon. Now let's talk about valence electrons. They're electrons in the outermost energy level of an atom. They're like the front lines of an army because they're the ones involved in chemical reactions. Valence electrons are shared or transferred during reactions. The number of valence electrons that an atom has is directly responsible for the atom's chemical behavior and reactivity. Here I have a picture of the sodium atom. It has a total of 11 electrons in which you can count all the dots, but for its outermost or highest energy level, it only has 1 electron. Therefore, sodium only has 1 valence electron. Before we move on, I just want to remind you of the different parts of electron configuration. The first number represents the energy level. This corresponds to the period number on the periodic table. There are 2 exceptions with the D and the F blocks. The D block starts at energy level 3 and F starts at 4. The letter represents the sublevel or the block. The superscript represents the number of electrons. Before we move on to the number of valence electrons, as a review, I want you to pause the video and write the electron configurations of these elements on your own. You can check your answers afterwards. Welcome back. Hopefully you have gotten these electron configurations right. Now we're going to count all the electrons in the outer energy level for an atom. Let's look at lithium electron configuration. It is 1s2, 2s1. 2 is the highest energy level in lithium. It has 1 electron. Therefore, we have 1 valence. Let's try with beryllium. Its highest energy level is 2, and it's got 2 electrons. Therefore, 2 valence. Boron's highest energy level is also 2. However, in this case, we got 2 sublevels within the second energy level. Therefore, we have to add up their electrons, and we have a total of 3 valence. Carbon, you do the same thing. Second energy level is the highest. We will add up the electrons in there to get a total of 4. For nitrogen, that would be 5. Oxygen, 6. 7 for fluorine, and 8 for neon. Now, let's do the electron dot structure for these elements. First, you write down their symbols. We're going to put valence electrons around these symbols to represent the dot structure. So lithium has 1 valence electron. Beryllium has 2, and I would write 1 on top, 1 on bottom to balance it out. Boron has 3, so I would just go clockwise. 1, 2, 3. Carbon has 4. 1, 2, 3, 4. Nitrogen has 5, so 1, 2, 3, 4. And now for my fifth, I'm going to go back and put it next to the first one, creating my first pair of electrons. Notice that there are 4 regions surrounding your letter that you can put these valence electrons. Each region can only contain up to a maximum of 2. Oxygen has 6 valence, so I would draw my first 4. The fifth would go with the first, and I'm actually going to put the 6th down here so that I have 2 pairs of electrons on top and on bottom, so it balances out, and 2 lone electrons on the sides. Fluorine has 7, so 1, 2, 3, 4, 5, 6, 7. And then neon has 8. 1, 2, 3, 4, 5, 6, 7, 8. This is the pattern that we use to draw electron dot structures. Now let's talk about valence electrons on your periodic table. The number of valence electrons for the representative element groups follows an easy pattern from 1 through 8 going across the periodic table from left to right. This means that all elements in group 1 will have 1 valence electron, all elements in group 2 will have 2 valence electrons, and then we're going to skip the D block because it's a little bit more complicated, and we move on to group 13, which will actually have 3 valence electrons. Group 14 will have 4, and then 5, 6, 7, 8. The only exception to this rule would be helium. It only has 2 valence electrons, therefore it would actually fit very nicely on top of beryllium, which also have 2 electrons. Notice that the elements in a group, also called a family, all have the same number of valence electrons. For example, group 1, which are called alkali metals, all have 1 valence electrons. Group 2, alkaline earth metal, will have 2 valence electrons, and they will have similar properties as well. These elements within the same group will behave in similar ways. Now let's try this. Find an element on the periodic table that has chemical reactivity similar to sulfur. This is sulfur. It is element number 16 on the periodic table. It is in group 16, and it will have 6 valence electrons. Any element that is within group 16 will then also have 6 valence electrons and a similar chemical reactivity. Finally, I just want to show you dot structures as represented on the periodic table. As you can see, dot structures are very similar within a group. They should be showing the same amount of valence electrons as dots. Once again, the only exception to this pattern would be helium, which would make it fit nicely on top of beryllium in group 2. Helium is actually still considered a noble gas, which is actually in group 18. That is it for the notes today. There will be a follow-up activity based on all these concepts you have learned.